Hi, good afternoon. Joshua here. Let's see. Okay, so I kind of have like a packed hour of stuff to discuss. And all that said, feel free to interrupt me if need be, if something doesn't make sense. Like my goal is for it to make sense, obviously. But if it doesn't make sense, let me know. So my general thesis here is, I'm just going to get right into it. My name is Joshua. You can call me by he and him if you need. And Amanda from White Coat Captioning is captioning this live. About a year and a half, 2 years ago, I had this question that I wanted to answer. I was doing some work for a client, and there was this question as to whether we could actually make a reasonable low-power LTE-M device. I'll talk a little bit more about that in a moment. And so this deep question in the back of my head is, how do we make LTE Cat-M, or how is LTE Cat-M so low energy? And actually, there's kind of a secondary question here, which is the data sheet says that LTE Cat-M is low energy, but data sheets do lying. It's very, here's the part where Pete from Nordic walks in and I call data sheets liars. So, so actually the secondary question that I have here is LTE Cat-M actually low energy? And another question beyond that is, what is LTE Cat-M? And man, this is getting complicated. I'd better have a stack of things to discuss. And so there's this other question, of course, which is, what actually is low energy? And so that kind of seems like an obvious thing, like energy low, right? That seems like the sort of thing that we should be able to answer trivially, but there's a little more nuance there. So the general question, backing all the way out here, is, if I'm going to be building an LTE Cat-M thing, how do I make my LTE Cat-M thing be low energy? And I'd like to know also, how low energy is that going to be? So if I'm building a device, and I want to know in the field how long this is going to last, this is the question that I want to answer before I go to mass production and put a bunch of these in the field. So the first thing, like the first kind of getting it out of the way thing, is this question of what is low energy? And energy definitionally, right, is the integral of power in time. But this is not actually, this is one of those things that seems sort of obvious, but has kind of non-obvious or counterintuitive consequences, right? And so if you look at these two different graphs, I didn't actually integrate the area under the curve. I just sketched these freehand. But you can pretend that the area under the curve is the same. But they're very, very different shapes, right? One of these has this big spike in the middle and then consumes no power the rest of the time. And the other is this constant amount of power. And so you could imagine that if I extended each of these graphs really wide, right, then if I extend this graph really wide, then we keep consuming lots, or we keep dissipating, or we keep consuming lots of energy eventually. And if I take this one and extend it really wide, then we're so close to the zero side of things that we don't actually meaningfully consume additional energy. And so the corollary of this, of course, is that power is energy divided by time, right? So if energy is power times time, then power is energy divided by time. And so, okay, let's just get everything straight for a moment. So like watts, we know watts is power. Watts times hours, okay. Power times time, that's energy, right? Joules, okay, that's the same unit as watt hours, just slightly different numerator. And then you start having really weird, okay, how many joules per day is this going to consume? Well, that's power. But Okay, how many watt hours per day is this going to consume? Wait, hours divided by days, so that's just watts there. Okay, that's power, right? Like, but the core element here is that the units look weird, right? We could just say put everything in joules or watts, but having these power times time divided by time actually enables meaningful mental distinctions in how we think about energy, right? And so this is right. What I was coming back to here was this idea of joules per hour, right? And okay, sure, joules per hour, we can make that a milliwatts or whatever you like. We can divide that. You can do the arithmetic, I suppose. But if I think of something takes X number of joules to idle for an hour, then I can start to think of that as an hour being a discrete event of idle time, right? Or if I'm going to tell you that it takes X number of joules later to go connect to an LTE network, then that's also okay, maybe that's a joules over a handful of seconds, right? But starting to think of things in terms of accumulating energy, even when time is in the denominator, is, I think, a meaningful way to think about this. And so the other kind of primer in this low energy kind of arc of thought here is there's three ways, if you think about this, to get low energy. One way to get low energy is have lower energy, right? One way to have low energy is if you're thinking about this as joules rather than as watts times seconds, then you can have lower energy by just use less energy in the unit impulse of whatever it is that you are doing. The other way to think about this, of course, is if you are separating this into power times time, then option one is you can reduce power while you are doing whatever your active thing is. And so and we'll come back to this later when we're talking about how LTE-M is low power, or low energy, excuse me, is how do they reduce the amount of power that they consume? And the other side of it is that you hurry the hell up. Right? If you do it in fewer seconds, and you take the same number of watts to do it, then watts times seconds, that's fewer joules. And so this isn't a new concept in wireless either, right? If you think about those two graphs that I showed you before, this is a common thing if you think about processors and C states and things like that. And back in the days when I was at NVIDIA, we called this race to sleep. Right, where getting the expensive thing is being off idle at all, right? And being off idle and having the clocks a little bit of the way up versus having the clocks all of the way up, you're actually better off turning the clocks all of the way up, finishing what you're trying to do, and try and turn all the way back off and switch everything all the way off. So this race to sleep concept is actually something that we'll revisit in a little bit here. But the most significant bit of this is you're designing a low energy thing. And I'm going to keep saying low power, and I'm going to be wrong. Because your power budget is actually mostly an energy budget, right? Your power budget, when you are saying how much power do I have to get a year of use out of this apparatus on battery, what you actually want to know is how am I going to divide all of the energy that is stored in this battery cell over the course of a year? You can just divide that by a year, but then you're talking about low power, and the reality is there's a lot of stuff happening in there, right? So okay, so that's the end of my shtick on low energy. Let's talk a little bit about, okay, so there's this question of LTE Cat-M. And so some good news about LTE is that LTE is a totally open spec. Here I have speaker notes here. Lovely. 3GPP is the third generation partnership project. It's a consortium. It's an industry consortium. Not to be confused with the 3GPP2. That's a third generation partner project 2, which was Qualcomm's play to have a completely competing set of specs against the 3GPP. The CDMA side of the world and the GSM side of the world. The GSM side of the world is 3GPP, CDMA is 3GPP2, and they're not on speaking terms, and 3GPP2 died, thank God. But in case you wanted more specs of this anyway, you can, this is also standardized through the European Telecommunications Standardization Institute. And also, if you look for LTE, actually they'll call it EUTREN, Evolved Universal Terrestrial Radio Access Network. So anyway, spec 36 series, right? LTE, LTE Advanced, LTE Pro. And yeah, here you go. That's some really nice crystal clear specs here. There's only 307 of them to read from. And don't worry, they're all versioned, and the version notes, you know. And the specs, of course, are crystal clear, right? This is obvious, straightforward. All of it tells you exactly what you need to know. An RRC connection suspend procedure is used at RRC connection release, whatever the fuck that is. Okay, I'm going to give you the gist of some of this here. So LTE, here's what you need to know. LTE is long-term evolution beyond what was the 3G side of the world. And beyond that is 5G, which is much closer to LTE than LTE was to the 3G side of the world. In lots of ways that I'm not really clear on, we don't have time to explain anyway. But that's one thing that you need to know. Another thing that you need to know is that LTE has a bunch of categories. The categories are of what it's a shared capability set between the cell, which is called the eNodeB, and the user equipment, your handset, your IoT device, your whatever, which they call a UE. So anytime you say eNodeB or ENB or something like that, think cell, and because this is a whole army of specifications that specify everything from the protocol layer down to the network layer, backing the whole thing, then actually an ENB refers to a very specific part of the radio stack. But for all we care about here, the cell is the cell tower is the eNodeB. And so if you agree on a handful of these together, if you agree on some modulation schemes and you say, okay, I'm going to support QAM64, or I'm going to support QAM128, or I'm going to only support QPSK, or I'm going to support an FFT yay wide, or I can do X many channels at a time, or whatever it is. When you agree on those set of specs, then then that's a category. So you can get a cheap non-IoT-ish category thing. That's Cat 1. The smallest you can get is a Cat 1 radio. And in order to, if you want, like this laptop here, I think has like a Cat 8 or Cat 9 modem in it, right? And so that's nearly as fast as 5G, huh? Funny thing that. Interesting. It's all just marketing. But anyway, so there are a handful of different categories, and some of this specifies how many antennas you have to have and all that sort of thing. And you can go read this in the spec, but I can't. But even the thing that you need to understand is that even Cat 1, which is the smallest that you can get in kind of LTE as LTE is resource intensive. You need a main antenna and a diversity antenna. Basically, you need to receive antennas in order to be a Cat 1 device. And so the question when they came along with all of this IoT LTE stuff is, can you have something that's, when I was writing these slides, I was thinking, can you have something that's easier? And the answer is no. LTE chapter, or 3GPP chapter 36, there's nothing easy about that. But can you have something that's lower energy, that is less, I don't want to say complex, it's still complex. But it's still annoying to implement, but it is lower energy to implement. And so what they came up with was two different things. There's LTE Cat M1, which I like to think of as like -1, but I think M is like machine to machine. And people will just call this LTE-M. And so the air interface layer for LTE-M is very similar to the air interface for the higher categories of LTE, right? It uses the same, I'll talk a little bit more about this later. Actually, I'm not going to come into this now. You get a megahertz and a half of channel bandwidth or so. We were talking about this yesterday in this room, I think. And the speed and feed on this basically is that you get more or less a megabit per second of bandwidth out of a single LTE-M UE, right? And that's theoretical, right? The actual bandwidth is probably a little bit less. But the other technology is narrowband IoT, NB-IoT. And so many modems, especially the one that I have on my desk here, will support both of these. But the thing that you need to understand about this is that the channel bandwidth is way, 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 way smaller. You get much less data throughput. And the other side of that is that the receiver bandwidth, that's RBW there, is much, much narrower, right? You need a smaller tuner. You need all sorts of stuff like that. And we're going to talk about Cat-M. A lot of these concepts apply to NB-IoT, and I don't know, if we have some time later, we can talk about LTE Cat-M versus NB-IoT. So now that we understand what LTE-M is, the question is back to, is LTE-M actually, like, is Pete over there lying in his data sheet? Or do these things actually work? Are these as good as they say? And so there's one way to do this. There's basically one way to find out, and that is go get an eval kit and get a power analyzer. And so that was really what guided my work here. And so there's tons of options, right? You can get Sequans makes a LTE-M module, Murata makes an LTE-M module, Nordic makes NRF9160, Quectel makes like 4 different Cat-M modules, uBlocks makes one that integrates somebody else's silicon and one that is their own silicon. So you can choose from those, right? You can choose from a bunch of different power analyzers. I'm using, that's the kind of thing that you can build yourself, by the way. And the other interesting question is, actually carrier by carrier, it really differs, right? T-Mobile has particularly bad LTE-M coverage, but they have good NB-IoT coverage. AT&T has good Cat-M coverage, and I have no idea how their NB-IoT coverage is. So which carrier and whether you get a MVNO or any of that, we can talk about all that stuff later too. But the stack up that I'm using here today anyway is I'm using NRF9160. Nordic aren't paying me for this talk. They probably could, and they wouldn't be too mad about what I'm going to say. The board, they sampled my client board. OT aren't paying me for this talk, and I'm going to trash talk them. AT&T aren't paying me for this talk, and I'm going to trash talk their entire industry. So anyway. Right, we'll come back to this modules and chipsets thing. I don't think we're going to have time, but we could talk about it later. It's in the backup slides. I think it is time that we do some experimenting. So what I have here is I have a Nordic NRF9160 eval kit. I have a AT&T SIM. I have an OT ARC power analyzer. And the question here is, what is the out-of-the-box power situation? No, I don't want that screen. Where the hell did my OT go? And I would like my terminal, please, which is over there. Okay. Let's turn on power. Flash the board. And we'll start recording. Ta-da! Okay. So let's just quickly do AT. I'm going to enter some commands. I'm going to tell you what the commands are. So this is a Nordic. So these are all AT commands. If you remember talking to an AT modem, you still talk to an AT modem with AT commands if you want to work with one of these things. The APIs that you talk to this programmatically later, you push it AT commands. But okay, so I've set it into LTE Cat-M only mode. There's a proprietary command to ask it to report signal strength. I've asked it to tell me when it connects to the network. Also asked it to tell me when it connects to the network. Signal strength again. And so if you're used to doing an ATD command for dial, that's not really how these work these days. AT plus CFun is enable functionality, turn on functionality. And ta-da, here's a current. So there's a graph of current up top. We are watching current from the modem. And I'm just going to let it settle down for a moment, and then I'm going to ask the OT to, and we're seeing some results here, by the way. We have registered on a network. Yes, we have definitely registered on a network, and we have some signal quality. I'll interpret those for you later. But right now, the modem seems basically stable. And so the question on my mind is, I'm just going to pause that, is, let's just average some of this here. I'm going to average this, and we are drawing, on average, 2.16 milliamps. I'm not super thrilled with that. I guess when I did this experiment at home, I was doing 2.3 milliamps, so, and that's what I did this math based off of. But basically, I'm doing truly nothing with the thing. I just connected it to the network, and I'm doing 2.3 milliamps. And people are telling me that I can get, years of battery out of AA batteries. Okay, so a AA battery is about 4-ish watt hours. An 18650 lithium polymer or lithium ion cell, like 9 to 10 watt hours. Okay, a UPS battery, 12 volts, 7 amp hours. That's 84 watt hours. Okay, so in order to run this for a year, I need a UPS battery. And so, okay, I'm going to go ask the datasheet what I should be expecting at least. And the datasheet is telling me that I am off by an order of magnitude here. And so that's, but at least somebody has done this before, right? Like now I know what I'm shooting for in my setup. And so, okay, so what is going on? Like, okay, those are good numbers, right? I would love to see order of microamps. That would be fantastic. And there's now the question of it's telling me PSM floor current in EDRX average current. Oh God, I don't know what that is. Let's ask. We're going to have to get some expertise in here. Okay, we're going to search Google. Google says LTE-M PSM EDRX. Okay. Wow, okay, so we have a lot of pictures that all kind of look the same. That, like if you look in the images, something is telling me there's something interesting happening here. Okay, so I found this resource. I really like this resource. These ShareTechN guys, like if you want to know how LTE works and want somebody to pre-digest the spec, I'm going to save you time. Read these guys' website. Because the website is, one, the website is a font of great content, and two, the website is absolutely covered in ads. And so in order to make sure that they monetize their website appropriately, make sure that you do not use your ad blocker. Anyway, this is the only diagram that I've taken from them, but I did want to cite it. So this is actually really cool here. So this is telling me normal DRX, whatever that is, and it's contrasting with EDRX. Okay, I'm gonna fill in the blank for you on what DRX is. DRX is discontinuous reception. And so that name has a core, that brings up a core concept in my mind of we're doing something not all the time. We are not turning the radio on and listening all the time. And so, okay, so we actually saw something like this. We powered the thing on, and there was a big current spike, and and something happened while we registered. Okay, yeah, registration. We registered on the network, and then we went into this kind of like spiky thing, right? Like periodically we woke up. But they're telling me with EDRX, extended discontinuous reception, I could make this really long here. I could make this gap interval here really long. Okay, And so in the back of my mind, I'll give you a hint now that this C is for continuous, or for connected discontinuous reception. We'll come back to that later. But when we actually start doing IP traffic. But we'll come back to this and we'll look at this idea. Long, but not extremely long. Got it. All right. So we've answered what is EDRX. The question is what is PSM? And the answer is we do not have time to talk about PSM. It's not that complicated. It's just not that interesting for what we're going to talk about. So now that we've asked the experts, Google has told us exactly what EDRX is. And I'd like to know how to configure the modem to do this. So there's this concept here. There's a set command, AT plus C EDRXS, and it tells me it sets the requested extended discontinuous reception parameters, blah, blah, blah. When an EDRX parameter is changed, the default paging time window is changed. What the hell is a paging time window? If other than the default paging time window has to be used, send that command. And here's the syntax for this command. All right, let's do it. So here's some commands that I'm going to send, by the way. Right, we talked earlier about some of these commands that I did send already. So CESQ is signal quality. SNRSQ is signal to noise ratio. Those are two different metrics. I think the latter one came in a more recent firmware revision. I don't remember it being there a couple of years ago. There's this. Okay, so I'm gonna set up a EDRX time of 10.24 seconds. It apparently is powers of 2 of hundredths of a second, because that makes sense. I'm going to set a paging time window of 2.56 seconds, and I don't know, we'll see what happens there. So let's try that. Show me, once again, go to live stuff. Let's just try this. AT plus CEDRXS equals 2, 4, quote 0001. Do it. So we just connected to the network to do something. Apparently we had to connect to the network to do something. And wow, we're spending a lot more time at idle now. And we seem to wake up, and we wake up a couple of times, then we go back to sleep. It's kind of cool. Let's try that paging time window command. So we're already starting to see that super long idle time show up there. Let's try this paging time window command. PTW equals 4, 0000. I imagine, oh yeah. So you can see there's a big spike there. It looks like we had to transmit something there. You can already start to tell by looking at the power analyzer when you're transmitting and when you're receiving, right? And so, okay, so I changed this paging time window thing, and there's only 2 spikes there now. So whatever this paging time window is how much we wake up, or how long we wake up for. Okay, that's kind of cool. And so let's try changing the EDRX time one more time. So we set it to 001 last time. Let's try 0010 maybe. Looks like we transmitted on the network again. And wow, we're really in idle for a long time. How long are we in idle for? Hey, look at that. It's pretty good. Okay, so in theory, we've now pretty substantially reduced the amount of energy that we're going to consume, I think. There are these big spikes in here, and the big spikes are much less frequent. So let's just average that. I'm just going to ask the tool to average this for me. Average on 1.81 milliamps. Wait a sec. Why, like, where'd the 6 microamps go? Hang on. I have what's this floor current here look like? My floor current is okay, so even when we're doing nothing, I'm drawing 1.71 milliamps. Okay, that's not fantastic. And so I went back to Google. And I found on the Nordic forums that they say that the big problem is that if I have the UART turned on, the UART burns a milliamp and change. Okay, and so this says that the Zephyr real-time operating system automatically can turn the UART on and off, but of course because I'm using the UART to control it over the AT command set, okay, well then it's never going to turn off. Okay, so what I'm going to have to do is I'm going to have to write something that emits all of these commands without turning the UART on ever. And luckily, the dev board has 2 buttons on it, and I can press the buttons. I can use the buttons to control when something is going to happen, right? Okay. Look, you guys, if you're going to, so 2 years ago when I did this the first time, I wrote my own wrapper function around a logging routine that set the UART disable bit. And that like stopped working recently in the latest, like when I unearthed this code and rewrote it. So I had to, so basically here's this lovely, well-documented flag that you set in the Zephyr config that turns off the UART when you're not using it. Here's some documentation improvement opportunities, I suppose. But okay, let's do that. Let's see if we can actually achieve the floor current this time. So I wrote some software to do that. Where the hell is my terminal? And disconnect from the network so AT&T doesn't get mad at us. Goodbye. Are we gone yet? Yes. Okay. Let's start over here. Stop recording, kill that recording. Goodbye. West Flash. Okay, so we'll turn the whole board off and we'll just start from scratch so we get a nice UART log here. Okay, so this is this test program that I wrote. And I'm already feeling a fair bit better here about this. Here is a floor current of 46 microamp. I'm feeling really quite a bit better about that, actually. And so I have this press button to turn on the radio. Let's do it. Come here, you. We are on the network, I believe. Yeah, we're on the network. We're registered on the network. And periodically, yeah, there we go. Okay, so we have our periodic EDRX spikes. So let's just measure this. And so also one kind of interesting thing that I'm seeing here, by the way, stop that. One interesting thing that I'm seeing here is that this spike kind of looks different than these 2 spikes. So I'm kind of wondering what that means. So I guess we'll come back to that later. But let's measure a whole EDRX cycle. Hey, 377 microamp. That's better. We're definitely doing better here. We're still kind of off by a little bit, by a lot bit, but yeah, when I did this experiment at home, I was hitting 100 microamp. So something interesting is happening there. But this is kind of close enough for now, at least. This is close enough. Like, we're starting to see how the process of low energy is really just chasing everything all the way down, right? And so kind of questions about like, where does this 100 microamp come from? There's other stuff leaking on the board. Who knows what it is? There are other OS configuration issues like that. Who knows? I don't know. I'd have to put the system all the way down. And kind of the really interesting one that isn't measured in the data sheet is the SIM card consumes a lot of current. And so depending on your carrier, AT&T, I thought they're supposed to have a decent SIM card, but I've seen SIM cards that consume like 30 microamp. I've seen SIM cards that apparently consume 100-ish microamp. So that's kind of interesting to think about. So now here's this question. So we've proven that it is possible to get low energy out of LTE-M. The question next is, when is LTE-M low energy? And so I wrote another test here. Again, we will turn off that. Goodbye. And we'll flash the board. So I wrote another test that does some UDP traffic. And this is where I think this starts getting really interesting. And I think so I really have two messages for you, right? My overt message for you today is that LTE-M is an interesting technology and you can use it and that's great. The covert message for you is that if you use test equipment that is not designed to be an educational tool as an educational tool, it's a lot more fun than reading the spec. And so, okay, I've just reflashed that. I'm going to power cycle my board. Goodbye. Yes, I'm sure, of course I'm sure. Power that back up, and I'm just going to listen for UDP packets on on a nice port there. I'm just going to listen for some UDP packets, and I'll power the modem up. And so this is the same thing, by the way, as the previous demo that I did, except this time when I press a button, it's going to send a UDP packet off to a machine that I have way out on the internet there. And so I'm going to let this first do a couple of EDRX transmissions here, or EDRX intervals here, I should say, just to show you what's happening here. And now I'm going to go transmit a packet in the middle of an EDRX interval. And so as soon as I hit the button, something interesting happened. And indeed, I got a packet here. I got a message. And you can see that eventually, so one thing that you're looking at is there's definitely like two different things happening on this board, right? One thing that's happening on this board is there's clearly this time that we are connected to the network and receiving or something. And there's definitely some time when we wake up and we do these huge current spikes, which have to be transmitting as far as I can tell. And then eventually we decide, okay, we're done, and we transmit okay, we're done, as far as I can tell. You know, this is, again, I haven't read the spec here, I don't know. But we transmit an okay, we're done. And we go back to whatever this low power mode is. So I'm just gonna respond. Here is a response. I'm gonna wait until the next EDRX cycle just so that we can see what's going on there. Yeah. Well. Whoa, okay. So we woke up and only right after the EDRX cycle did we get our response packet. So that's kind of interesting, but also it was only after that first spike we missed the first spike. So that first spike is clearly different. Maybe, I don't know, let's try. Here is a response, and let's gonna send it between the second and third spikes. Okay, so the third spike, right? So we can catch, so we're starting to understand, we're getting a intuitive feel for what's going on here. And this is the cool thing of exploring this way, I think, is that you can read this in the data sheet, or you can have a more intuitive feeling for how this actually starts to go together, right? I now have this intuition that first one that is different doesn't actually seem to listen for anything. And this concept of a paging time window is the amount, there's this concept called paging, apparently. And paging must be the thing that you do to wake up a modem or to wake up a UE, I guess they call it, that is asleep. So, okay, so we are now doing some sort of paging in order to wake us up. So this is a cool concept. And now I have this other question, which is, this is fantastic. I'm having a great time here with my board on my desk, and devices don't usually stay on desks. If they did, then we would plug them into the wall. So in some senses, that's not super useful. Okay, let's turn off the power. Sorry, AT&T. I'm gonna load here instead, since I can't go for a drive. Oh my God. Since I can't go for a drive right now, I took this in my backpack while I was on a Caltrain on the way up to San Francisco. I live in Mountain View. And so here's this session going on, and I can replay this trace in the OT. So let's just start looking and picking and see what's interesting that we can find. So one thing that is interesting is this spike is kind of differently. Remember, we're looking at these 3 spikes, and we think that these 2 have to do with actually listening, and this has to do with something else. Who knows? Sometimes this something else takes a really long time. Like there's more something else to do. And actually, when that something else happened, the modem told me something. It said CESQ 255, SNRSQ 127. What the hell does that mean? Hey, I'm glad that somebody put that in the slide deck. This basically tells us bigger is better except when it isn't, is the signal to noise ratio. And the second number is bars, I guess. And I'm going to ignore the rest of this for the time being. And also there's CESQ is a different thing that measures kind of the same thing. Rather than signal to noise ratio, it measures absolute power. So anyway, basically what I'm hearing is that bigger numbers of these are better, and really big numbers that are like uint max or int max are not better. Those are anti-better. And so if we see those, then we have bad news. And hey, while we're at it, let's man, thank you, Joshua, for putting that in the slides. CE reg, here's another message that the modem could send us. So if we get a 1 at the beginning, then, or I guess a 5 at the beginning, we're good. Anything else, we're not on the network. Okay, sounds good. And then there's this other thing here that's interesting. I'm actually going to ignore the rest of this crap. You can read it if you like. There's a tracking area code, and there's a cell ID. So basically, in theory, every time we switch from one cell to another cell, then it'll tell us, I think, what the new cell that we're on is. And it will tell us also this tracking area code, whatever that is. Yeah, we can talk about tracking areas later, I guess. We can put that on the back burner there. So let me go back to this real quick. I'll kind of breeze through this a little bit here. So what happened here is that the modem seems to have woken up and decided, hey, wait, there's no signal anymore. And then shortly thereafter, it goes, oh, wait, hey, never mind, I found a signal. Everything is fine, my bad. And right afterwards, it tells me right at the same time, also, hey, I moved to a new cell. Okay, so this is cool. What we have learned from this, remember that we can see the difference between receive and transmit, right? And what we have just learned from watching this is that you don't actually need to transmit to say, I've moved, right? I'm on the train, I've moved. It said there's no cell, there's no service. Oh, never mind, I found a tower, it's a different tower. And I haven't transmitted at all. Somehow, we're back to just listening again. Okay, that's an interesting insight. So let's hear a little bit more about what the modem has got to tell us. Yeah, lovely, lovely, very good. So here's another one of those events where, okay, that definitely went wrong. There was, I guess I'll call that a cell reselection. We can call that a reselection, where it goes and it must go and listen to a handful of different cells. It tunes each one and tunes a handful of different channels and decides what the best one is. Okay, now it's decided what the best one was, and it tunes in, and there we go. Okay, lovely. And so that's kind of cool. I'm going to zoom out a little bit more here. There's a handful of more interesting events. So we're just hopping along from cell to cell, and something kind of interesting happened in here. What happened in here? I don't know. The modem had to wake up for some reason. Can't tell you why. That's another reselection. So here's kind of an interesting looking event. What happened? We're not doing EDRX now. Actually, we woke up and we did some transmit traffic here or something. Maybe, I don't know. Okay, so what's happening is we changed cells and we really fell off. So we got the registration of doom message. There is no cell anymore, goodbye, screw you. Never mind, sorry, we found a cell again. Okay, we looked really hard. We spent a lot of time looking and we found a cell. Okay, great. and hey, the cell went away again. But don't worry, we found a cell. And this time, without transmitting anything, somebody turned off our EDRX. We got a message saying that there's no EDRX anymore. And now we have to wake up for a while. So now all of our low power gains there have kind of walked, or low energy gains have walked away from us. So that's kind of frustrating. So what we can learn is that what we've learned from watching, again, just watching, is that the cell can autonomously, or the cell tower can autonomously tell us, screw you, no EDRX on this cell. And so a little while later, we come back along. Somewhere in here, we went back to EDRX land, apparently. Yeah, look at that. Yep, OK, EDRX is turned back on. We're fine. Oh, man, that's a really bad cell that I was hanging out in for a while, apparently. And so the other event that I wanted to show, yeah, this one's a cool one. So first off, I want to show you the last time we registered on tracking area 8 Bravo 42, Foxtrot 80 Foxtrot is the cell. And so something interesting happened in here. We changed to tracking area 8 Bravo to Foxtrot. So what we've learned from here is that there is this concept. So sometimes the tracking area does change. And when that happens, we have to do this. This is a case where it's hard to see the difference between transmit and resume, and transmit and receive on this graph. But we actually did have to transmit this. There's a thing called the tracking area change. And it happened here. And so this is the core concept of why you don't have to transmit to move from cell to cell. If you're within an entire tracking area, then you go broader and broader from the last cell that you were seen on up until you hit the edge of a tracking area. And then you have to wake up and tell the network, hey, if you're looking for me, I'm over here now. And that's a transmit event. So, right, so here's this kind of, like a recap of kind of what we've seen with this analyzer, is we've seen floor current. We can see where the thing is doing absolutely nothing. We've seen what the concept of a paging interval is. We've seen the concept of we had to measure what changed, right? We've seen, actually, I'd never seen this happen before I started doing this set of tests, is sometimes you can lose in terms of EDRX. Sometimes the cell can tell you, no EDRX on this cell, you better keep waking up. And we've seen through all of our measurements this idea of a kind of a quick session setup and a long session setup. You set up a session to do some transmitting, and then there's this pattern, and then you go back to sleep. So with our 9 minutes left together, I'm going to kind of whip through a handful of other stuff. But the question that I wanted, this is the thing that I think is really cool. So, OK, actually, before I get to that, I'm taking away from the 9 minutes that we have left together. This is the other thing that I think is really cool, is that we saw all of this and we learned how the network works only from reading what the AT commands are and what the OT box has. The OT box, I said I was going to dunk on them, now is a paid subscription model test equipment. Ha, ha, ha. So buy something else now, I guess. I think Nordic makes a power profiler kit that can do a similar thing. It has less wide range than the OT box. The OT box is a 2-quadrant supply if you want it to emulate a battery, and if you want to pay them monthly for the privilege of its sinking current instead of sourcing current. Just like, what the hell, OT? But anyway, so either way, whether I like the tool or not, or whether I like the makers of the tool or not, it was a lot more fun than reading 302 specifications. So question one, that we're popping things off the stack finally now, is how is LTE Cat-M, like how do they do this, right? And we're back to this idea of energy is integral of power d time. And so if you want less you can reduce the power to get less energy, you can reduce the time, get less energy. And so we learned a little bit about each of these, like how does LTE-M reduce the amount of time? We do the hurry up and wait thing, right? The race to sleep thing is we have discovered that we have variable latency, right? If you are right awake right then, I didn't show you this in the UDP demo, but if I sent you a second packet right away after you'd woken up, then you would have received it very quickly. You wouldn't have had to wait for another paging interval. So if you're doing a lot of traffic, then you can keep your latency low. And if you know that you're not going to be doing a lot of traffic, then you can opt to have as much latency as you can tolerate. And because everybody in the system agrees, right, it's not the Wild West, and in fact the agreement is specified by 302 specifications, everybody agrees to listen at the same time, so we can do these extended listening intervals. And I didn't show you this, but we can talk this RAI thing, and we'll talk about it later if you want. Like corner me later, I don't know. We don't really have time for it. But the other question is, how do you reduce power for LTE Cat-M, right? So LTE Cat-1 requires antenna diversity. You have to have 2 antennas. You have to process signals from both antennas. LTE Cat-M, there is one and only one antenna. You get the best of one or one. You can receive one way or one way. And so that means that you require half the receivers, which is probably good. And if you were in this room yesterday, we talked a little bit about the concept of using a fast Fourier transform. So this is, for radio nerds, enjoy this. For non-radio nerds, I apologize. So the core concept is that LTE does, if you think of like an AM radio, or if you think of, I think Bluetooth LE is this way on the left there, you transmit a thing at a time. You transmit 11111010, right? You transmit a code word or a symbol at a time. The core concept of OFDM is that you transmit each symbol for longer, but striped across the frequency spectrum. And you may go, why the hell would you do this? Like that seems like it is more complicated, and you would be right, except that there is this concept called a fast Fourier transform. It took me, so I took a signals and systems class in undergrad, and then it took me 8 years of crystallizing to understand, to like actually understand how this all goes together. I didn't get it then. It really took me a long time. But if we kind of treat it as a black box for now, one way that you can use less power is you can make each of those individual symbols less expensive to demodulate, right? You're striping all of these symbols and you're demodulating them all at the same time. And so traditionally you might be able to cram 8 bits per symbol or something like that with a really deep constellation, they call it. That's QAM 256. And let's say actually that we only want to fit 2 bits in there. That's quadrature phase shift keying. There's do. Why the hell are there 2 axes? For reasons. But the answer is, okay, I can cram 2 bits in there. And that's a lot less data that I have to deal with, right? So that's certainly one way to reduce the complexity of my receiver. Another way I can reduce the complexity of my receiver, I kind of lied. Right, yeah, big brain idea, right? Big brain, have simpler symbols. The reality actually is that OFDM is not actually 4 wide. It's actually like 4096 carriers wide. I didn't put 4096 carriers here, but you get the idea that it's quite a lot wider, right? Well, what if you didn't have to demodulate all of those carriers, right? What if instead of demodulating all of those carriers, like expanding brain, right, you only demodulate 4 of them? Okay, that's great. That's a lot less data that you have to process each symbol. And so the truly galaxy brain idea is that you can this is like my favorite concept in LTE-M as a radio nerd, is that you can do a smaller FFT. You don't have to do the O in OFDM stands for orthogonal. And so that means that you can do a 4096 wide FFT if you want to see all of those, or you can do an FFT on just a handful of channels at the same time. And you don't have to change the transmitter. So my phone can still do a 4096 FFT on the same thing as this is doing a 16 FFT or whatever. And good luck with your bandpass filter. So the question anyway is, here's this core, running out of time here, but the core question is, how much energy is your app going to use? And the answer is, think energy, not power. There are these discrete operations that happen. I am moving from one cell to another cell. I have to do cell reselection. I'm changing tracking area. I'm waking up to transmit. And yes, then there are the power things that I encourage you to think about as energy. I am at floor current for an hour. How many hours per day? Well, they're 24 hours per day. Okay, right? So start adding, get your Excel spreadsheet out, right? And start coming up with a model of this. The lifetime energy is just a summation of all of these, right? Of the energy of each event times the number of times each event happens. And if you want to use less energy, then you do fewer things that are expensive, right? If you find that the individual EDRX spikes are expensive, then do that less frequently. So here's the part where I plug for myself right at the end. I'm half of a little two-person consultancy. And I did the original research for this. So I redid all of the research for this for TEARDOWN. I used none of the IP that I wrote for my client. So this actually took me an enormous amount of time to prep for this. But this kind of research and explaining things in this way and building cohesive projects and products and all that kind of stuff, that's actually what I do. That's kind of my specialty. And so if you have a company that needs somebody to do research of this kind of nature, or you need to do system architecture on how to build a low power thing, or need somebody to actually write the code or hook it up to a power analyzer or lay out the board or whatever it is, then my business partner and I can probably do this for you. And so that's on an FPGA level, software level, hardware level. Anyway, this is my plug for myself. I have business cards, and it is now snack time. I have backup slides, and I'm just going to send a link around later. Yeah, like here's, right.